Hi everyone, I'm Benjamin Zhu. I'm glad to be here to present our highlight paper, ConQueR Contrast Voxel-DETR for 3D object detection, or ConQueR. DETRs have revolutionized object detection with its transformer architecture and one-to-one matching, but its set matching laws only supervise each query individually without considering inter-query relations. Moreover, its fixed top-K outputting scheme causes duplication in the final detections. To tackle this problem, we propose query contrast, which explicitly enhances each GT's master query and suppress predictions of all other unmastered queries during training. Specifically, we encode both queries and GTs into a unified latent space by the transformer decoder layers. In this space, we construct positive and negative GT query pairs based on the Hungarian matching results and conduct contrastive training to achieve our goal. ConQueR achieved remarkable detection performance and improved sparsity in the final detections. Now let's get into the details. Our objective is to identify all objects without post-processing given the point cloud inputs and achieve state-of-the-art performance. Previous works based on whether they require post-processing like AMS can be categorized into dense detectors and sparse detectors. Dense detectors usually have a strong performance, but their structures are rather complex and cannot be end-to-end optimized. On the other hand, sparse detectors usually have a clean pipeline and can be optimized in an end-to-end manner, but their performance still largely lag behind dense detectors. We point that DETRs usually adopt more queries than GTs in a scene. For example, there are usually 40 objects in a VMO scene, but we usually adopt 300 queries to guarantee the recall rate of the final detection results. This inevitably incur many false positives during inference. Here we visualize an example scene in VMO. We find that most false positives are highly overlapping in local regions, which is caused by the lack of explicit supervision to discriminate and suppress local similar queries. We first build a simple and strong baseline named Voxel-DETR. It takes in voxelized point cloud as input and use a sparse ResNet FPN backbone to extract dense BV features. These features are further processed by the transformer encoder. Then we introduce a class-agnostic RPN network to generate top-scored object proposals. These proposals are served as initial queries to the transformer decoder layers. In the transformer decoder layer, we conduct iterative refinement like a deformer DETR, and during inference, we select top-scored predictions of the final layer as our final detection results. And for the query contrast, it was applied to each decoder layer. Now let's get into the details of query contrast. Query contrast consists of two steps. The first step is the construction of positive and negative GT query pairs. And the second step is how to contrast positive GT query pairs against negative ones. In the first step, to determine queries to be enhanced or suppressed for each GT, we first construct positive and negative GT query pairs by reusing the Hungarian matching results. Given one GT, the query with the minimal matching cost, that is, the blue master query, forms a positive pair with the GT. All other unmatched queries with this GT are then formed negative GT query pairs. These GT query pairs help us to identify the object query that need to be further enhanced or suppressed in our Voxel-DETR. So this is the first step. In the second step, we need to contrast positive GT query pairs against negative ones. Before applying supervision to the positive and negative GT query pairs, we need to quantitatively measure the similarities of these pairs. However, simple geometric metrics like IOU cannot sufficiently model the similarities between GTs and queries. We thus propose to embed both GT and queries into a latent space for comprehensive similarity measurement. In our Voxel-DETR, both object queries are formulated as object proposals, that is, object category and box location, size, and orientation. Therefore, the transformer decoder can naturally be used to encode both GTs and queries into a unified latent space. We simply select the output layer of the FFN prediction head after each decoder layer, followed by a shared MLP for similarity estimation. However, we also observe that the distribution of GT objects and query boxes can be quite different, especially in the early stage of the training. To mitigate this distribution gap, we apply a projector to query embeddings to align query embeddings to GT's embedding. With aligned GT and query embeddings, we now can estimate all positive and negative GT query pairs similarities. Here we use the cosine similarity metric. And then, based on the similarity, we can naturally use the info NCE loss to encourage the best matched query to generate more accurate predictions towards towards this GT. And all other unmatched queries are forced to deviate away from this GT. During inference, we abandon the fixed top K outputting strategy and use a score threshold to filter out low quality predictions. Here is the experimental results of our work. Query contrast significantly improved the detection performance and sparsity of final prediction. It closes the gap between sparse and dense 3D detectors and sets new records on the challenging Waymo open dataset benchmark. With the help of query contrast, our ConQueR achieved state-of-the-art performance. ConQueR also achieved overwhelming performance on the pedestrian and cyclist category. And with our score-based outputting scheme, the FPs can be greatly reduced. And as the model gets stronger and stronger, the false positive can be further reduced by our query contrast strategy. So ConQueR shows great potential in reducing false positives. Okay, that's all the content of our work. Thanks for your listening.